Okay. Hello everyone. My name is Chen Ye, a first-year PhD student from Shanghai Jiaotong University, supervised by Professor Bingbing Li. This video introduces my work published in ICCV 2023, Editable Image Geometric Abstraction, a Neural Primitive Assembly. Okay, geometric abstraction is an art form that has been studied for a long time, popularized by influential artists including Pablo Picasso. Geometric abstraction dedicates to represent the world using composed primitives that are either purely geometric or elementary, which has a far-reaching impact and is favored by highly frequent applications such as graphic design, industry design, cartoon production, and modern arts. This work explores a novel deep learning-based image geometric abstraction paradigm based on assembly out of a pool of predefined simple parametric primitives like triangle, rectangle, circle, and semicircle, facilitating controllable shape editing in images. Okay, we define such a problem as a bipartite imaging problem between two parametric sets. One set is a primitive type set, and another set is a shape attribute set, where the shape attribute set includes a fine transformation coefficients and color information for specific image areas. And our task is to yield a primitive alignment matrix A, with each element determining if an alignment exists, and each alignment moves the corresponding primitive to a specific area in image, and then rasterize it to pixels with corresponding colors. Our problem can be formulated as equation 1. However, there are three main challenges for our task. The first is a high dimensionality. Compared to sketch-based methods that only need to predict control point locations, geometric abstraction requires selection of primitive types, leading to exploiting searching space. In addition, more complicated transformation parameters such as fine coefficients and colors need to be predicted simultaneously, which further expands the optimization space. And the second challenge is non-differentiability. The non-differentiable nature of primitive selection, together with primitive to pixel rasterization, double the difficulty in employing any off-the-shelf deep learning framework. The third challenge is the weak separation. In this work, we only have rasterized images for training, without any image to vector or image to primitive labeling. Therefore, the primitive alignment task is an unsupervised setting, since large-scale, high-quality artistic images in vectorized format are extremely difficult to collect. And here is our framework. To overcome the high dimensionality challenge, we follow DETR and Paint Transformer to utilize the transformer encoder to predict the shape attribute set, including affine transformation parameters, shape colors, and primitive type distribution. For the non-differentiability, we propose a novel neural software alignment algorithm. And for the weak separation, we utilize the differentiable rasterization technique to rasterize all transformed shapes together into pixels and compute the L2 pixel loss with the input image. For the neural software alignment algorithm, we first review the differentiable rasterization methods, where opacity values are always defined to describe the degree to which content behind an element is hidden. Inspired by this observation, we propose a relaxed bipartite imaging objective. The core idea is that the output probability of all possible primitives at each position will serve as the opacity value so that all possible candidates can be combined and then rasterized together just for once. And the final render pattern is the opacity value weighted combination of all primitives with the same transformation and color attribute, as shown in equation 3. In this way, we can greatly reduce the number of rasterization times for different candidates during optimization and make it easier to better propagate the gradient towards the primitive closest to the accurate shape, as shown in the figure. And our optimization objective can be formulated as equation 4. This page shows some correlative results of our method. We compare our framework with state-of-the-art like Clipasso and Esclip for geometric abstraction task. The results reveal that sketch-based abstraction cannot exploit the diversities of image geometry, and it is important to abstract images geometrically with simple geometric shapes. ESClip creates great shape redundancy and fails to abstract images effectively with limited number of shapes. Our method realizes efficient geometric abstraction through assembly of predefined primitives, and our framework can serve as a useful tool for modern graphic design. Considering that our method represents images with vector graphics, we also evaluate the quality of generated vectors and compare it with sorter methods. We see that our method is capable of generating regular vectors to exploit fine-grained image geometry. In addition, existing image vectorization methods are not convenient for image editing, while our method has straightforward image editing ability, benefited from regular geometric primitives. And our framework also has some valuable extensions. We also visualize the shapes generated by different transformer decoder slots. We can observe that each decoder slot learns to centralize on specific areas, which motivates two interesting extensions of method. For example, we can transfer specific semantics to different geometric shapes by directly replacing the corresponding primitive type during inference. For example, star eyes can be achieved by simply replacing the primitive with a parametric star shape. Also, our method overcomes the disordered nature of previous image vectorization methods. We can perform interpolation between two predicted vector graphics and generate novel art images by simply interpolating the points of each predicted shape in order. We see that our method can interpolate not only areas with rich semantics, like eyes and mouth, but also the face poses. And here are some more visualizations on various datasets. To conclude, this work proposes a novel and efficient image geometric abstraction paradigm in an unsupervised and differentiable manner. Experimental results on various datasets and tasks demonstrated that our framework generates accurate and regular vectors to exploit geometric information of images with combination of only 4 simple primitives, facilitating straightforward controllable shape editing by simple editing primitives during inference. In the future, we are dedicated to collecting a more diverse and comprehensive dataset for image geometry abstraction tasks, and we also intend to generalize this framework to more general image vectorization tasks. Thank you for listening.